Let's describe two position functions of very different forms and clarify a bit what those position functions are going to tell us about velocity and acceleration. So let's start reasonably simple. Now, hi, algebra-based physics people. I just weirded you out with meters per second cubed. You haven't seen anything in meters per second cubed before. Just hang tight with me for a bit with that. Okay. Let's take this function. Let's determine average velocity between time equals 1.0 seconds and time equals 3.0 seconds. Okay? Now, average velocity is our old definition. It's delta x over delta t. But that's going to mean we need x at 3.0 seconds. And we're going to need x at 1.0 seconds before we can actually deal with the 3.0 seconds minus 1.0 seconds story down here. So let's do a couple of computations. What's x at 3.0 seconds? Well, that's going to be 2.0 meters per second cubed times 3.0 seconds quantity cubed plus negative 4.5 meters per second squared times 3.0 seconds squared plus 6.0 meters per second times 3.0 seconds. This is 2 times 27. That's 54. That is negative 4.5 times 9. That's negative 40.5. And then the end is 6 times 3, which is 18. So x at 3.0 seconds is equal to 31.5 meters. The seconds cubed cancels out seconds cubed here. The seconds squared cancel out seconds here. And the units here are behaving not as specifically meaning anything. I still don't know what meters per second cubed means, but they're as coefficients that are canceling out quantities in the computation. So let's do 2.0 meters per second cubed times 1 plus negative 4.5 meters per second squared times 1 plus 6 meters per second times 1. And that is 2 plus 6 minus 4.5. Well, that looks like 3.5 to me. Let me double check that. Yeah, 3.5. So the average velocity for this story is 31.5 meters minus 3.5 meters over 3.0 seconds minus 1.0 seconds. Looks like 28 over 2 to me. Looks like 14 meters per. Yeah, I had that right. 14 meters per second. And that's average velocity in that period of time. Well, that's just good old-fashioned algebraic functional thinking. Okay? That's just taking in the specific story that's been told and applying some functional thinking to it. Let me actually see if I can grab this a little bit more intelligently. Good boy. Well, then, what I want to do is I want to know an instantaneous velocity in that period of time. So let's talk about for this same function that we've got. For this same function that we've got, good boy, come here. Hey, how you doing? Let's talk about an instantaneous velocity. At 1.0 seconds. And 3.0 seconds. Okay. Well, if we're going to do that, we need to know v of t as the time derivative of the position function. So we're going to do our standard derivative each of these times. We're going to do 2.0 meters per second cubed times t cubed times the 3 there. 3 comes down. That's going to give me 6.0 meters per second cubed times t squared. Plus, I'm going to square the 4.5 here. That's a negative 9.0 meters per second squared times t plus 6.0 meters per second. Okay? Well, at t equals 1 second, v of 1 second is going to be 6 times 1 minus 9 times 1 plus 6, which is going to be 6, negative 3 plus 3. Practice that and see if you're confident enough to do that in your head. If you have to write it out a bit further, you can do that. At t equals 3 seconds, the instantaneous velocity is going to be 6 times 3 squared, 6 times 9, 54, minus 9 times 3, 27, plus 6, that's 33. Again, confirm that and see if you've got that. Note that in our old constant acceleration kinematics, the average of two velocities at the endpoints of our time should always come out to be the average velocity for that time. That's not working so well here. The average of these, let's do a red for this. 3 and 33 over 2 36 over 2 is 18. Which is not equal to V bar. And why in the world is that not true? It was always true when we did constant acceleration kinematics. But one of the things that I have to tell you coming in the door right here is this isn't constant acceleration kinematics. Okay, let's do one more time. Okay. Oh, behave, good boy. Come down here. Okay, there's my position function. And let's add to this my velocity function. V of t is going to be 6.0 meters per second cubed times t squared plus negative 4.5 meters per second squared times t plus 9.0. Sorry about that, y'all. Let's fix it. 2 times 4.5 is 9.0. That's better. Plus, that's just still 6.0. Okay. The acceleration function is just the second derivative of the position function, the derivative of the velocity function. Let's take the 2, bring that down in front. And I've got 12.0 meters per second cubed times t minus 9.0 meters per second squared. And the 6.0 meters per second term goes away. Oh, hi. That's not constant acceleration. That is an acceleration that is changing as a function of time. That's an acceleration that starts out going backwards, slowing down at a rate of 9.0 meters per second, but very, very quickly turns tail and represents something that starts speeding up. And the 12.0 meters per second cubed gives a picture of how quickly the acceleration is changing as a function of time. If you get really sophisticated in studying this stuff, you find that there's a term jerk that represents that 12.0 meters per second cubed. We won't talk much at all about jerk. It's not a useful idea for most of the applications we go through. But the principle that we're imposing here of doing these successive differentiations dx dt to get to v, dv dt to get to a, that is something that we will come back to. And making sense of units for strange things like this is something that we will come back to. Now, this is an example of a story where we have successive functions of time that we've gone through differentiation, where we have numbers in place and the numbers have representation. But from time to time, we're going to want to go through a process that is exclusively symbolic in nature. And that's the other story that I want to tell. That probably will take some of you into material you've worked through in an algebra-based physics 2, or maybe an algebra-based physics 1 if that physics was very aggressive. Let's talk about a different initial function of time, one that isn't a function that has a neat polynomial form. But let's talk about a function of time where we have some initial x multiplied by a cosine function. And I'll keep this very simple for our initial approach. I won't bludgeon you over the head with chain rule stuff that's sophisticated quite yet. I'll get there. Okay? But let's talk about a position function of time that's equal to some amplitude, some initial position, times a periodic function, a cosine function. And what does this look like when it's plotted out? It looks periodic. Cosine function starts from 1, goes through to 0, minimizes, comes back up to 1, repeats itself over and over again. I shouldn't say 1, I should say this is x naught here. And because the cosine itself goes from 1 to negative 1, well, what's down here is negative x naught. And we go through the up and down. Well, v of t is equal to dx dt. Okay. It's not neat to do with the t buried in the cosine function. Many of you know that the derivative of the cosine function is the negative sine function. But the omega, how do we handle that? Let's take the cosine of omega t and define it as u. Or take omega t, excuse me, and define it as u. Okay? So what we can do is we can take the derivative of x with respect to u, then take the derivative of u, he said, with respect to t. That's a chain rule. And if we do that, then x of u is going to be equal to x naught times the cosine of u. Well, there's my negative sine function. And the derivative of u with respect to t, well, the t just goes away. I'm just left with w. I say W, I mean omega. I'm trying to do Greek here. So V of t is equal to negative omega x naught times sine of, replace back u, omega t. And when we do this derivative, we talk from time to time about the omega popping outside of the function we're working with. I'll just sketch out what that. I'll put this sketch out on the next page. X of t is equal to x naught cosine omega t. V of t equals negative omega sine. Try that again. Negative omega times x naught times sine of omega t. Now allow me to do my v of t function. Starting from 0 as a sine does, starting out going negative and coming back positive, going negative, coming back positive, and so on. And this right here is negative v max, and up here is v max. And v max, the maximum possible velocity of the oscillator, is just the coefficient of the sine function, omega x naught. And we can repeat that taking of the derivative with v of t to get a of t. A negative omega is going to pop out. You can do the same exact chain rule work again to see how that omega is going to pop out again, give us omega squared up here. And then the derivative of the sine is the cosine. And we can build an a of t function starting from the negative max acceleration. If I was doing this properly, I'd have these guys perfectly aligned with one another. I think I've botched the perfect alignment somehow, but you see the shape that these are coming through. That's a negative a max there, that's a max there. And the maximum acceleration then is omega squared times x naught. And you can see working through these stories how we use the derivative to work out functional forms, not just of polynomial position functions and velocity functions, but of sinusoidal position functions and velocity functions. And having this sense of how derivatives work in our benefit is going to keep us moving. Now, of course, if we're doing full calculus-based stuff, we don't just want to do derivative stuff. We want to do integral stuff as well. And I need to give some explanation to that.